So in this video, we'll review Castigliano's theorem and strain energy for deflection analysis. And so what I want to highlight here is just a reminder that if we consider how the force or the loading is producing a deflection, we can describe that energy being stored in the member. So the loading is causing a deflection, and this loading is linearly increasing with deflection, right? Or vice versa. And so the energy there would be the integral on this graph, if we consider back to our definition of work. And so that would be 1/2 the force times the deflection, or we can describe the slope there as the spring constant. And so there are some, I'm going to kind of skip over here to some common strain energy formulas. We have axial, torsion, direct shear, transverse shear, and bending, right? And then the other thing that I wanted to highlight here, a couple of things. When we are dealing with transverse shear, we have a cross-sectional correction factor that we can consider, depending on the cross-section of the object, and that would just go into the C value here for transverse shear. And the other thing I would point out is that if everything's constant, we can describe the strain energy due to all these constants, but if anything is changing along the axis, we can integrate. And so if the area is changing, or if the force is changing here, if the moment is changing, we can accommodate for that in this relationship. And the reason we want to do that, and I'm just going to jump down to Castigliano's theorem, is that the derivative of the strain energy with respect to the force of interest is the deflection due to that force. And so if I can describe the energy due to a cantilever applied force, or if I can describe the energy due to a distributed loading across a beam, whatever it might be, I can then take the derivative of the energy with respect to that force and solve for the deflection. And so example 4.8 does the energy portion of this, where the energy is a function of the shear and the bending, and you can see here that the bending is described as F times X. So in our cantilever beam, we're going to start at and so we can describe the length of the beam, but then we can describe the distance x here. Okay, and so that's what I was looking for, was our axis. So our moment is F times X, or negative F times X, and so we can integrate and get an expression for the energy. And then using Castigliano's theorem, I can differentiate the energy once with respect to the force and get the maximum deflection, because this expression for energy is the total energy of the beam. So this is going to be the maximum deflection at the end. And so the other thing that they point out in this is that often the shear is nearly negligible, but we can deal with that on a case-by-case basis. Now, example 410 is looking at a shaft that has 2 diameters, and so it's cantilevered here at C. It's the applied loading is at A, and at B there's a change in diameter, and they give us the inertia of BC to be double the inertia of AB. And the question is, what's the deflection at A, and what's the deflection at B? And so there are 2 pieces to this that we're going to look at. And one is the fact that there isn't a force at B, and so that complicates our analysis. But the other piece is that we have a change in the diameter at B. The final piece here that we're looking at is the fact that we can skip a step in using Castigliano's theorem. So by describing the deflection as the derivative of the energy with respect to a specific force, so this is the deflection due to a particular force, I can rewrite this, given that this is the definition of energy for bending moment, for example, and then I can evaluate my partial derivative with the only thing that's changing here with respect to the force, and that is the moment. And so I can rewrite my deflection it directly in terms of this integral without having to artificially pausing and generate a expression for the strain energy. And so 3 of them are shown here, although this is not exhaustive. So 3 of the possibilities are here, and what we're looking at in example 410 is how we can use the bending due to load F, and how we can break up this integral to deal with the fact that it's different A to B than it is B to C. And so if I break this up here, what I'll look at first, delta A is fairly straightforward. I have, I'll start x at A, so x0 is at A, and it increases to the right. And my bending moment is equal to negative fx, which means that my derivative of the bending moment with respect to the force F is equal to negative x. So we will take the integral from 0 to L over 2, and we'll plug in negative fx and negative x as my moment and my derivative of moment with respect to f. Then I will do the same from L over 2 to L, same bending moment, same derivative. What changes is our inertia. So here we have I1 and here we have 2I1, and now we can simply evaluate this for the deflection at A. The complication is the deflection at B. And what we'll look at here is, what if we apply a fictitious force Q, and when we're done applying it to our expressions, we'll recall that it's 0 and remove it from our final expression. So if we redefine the definition of, or redefine our bending moment, from A to B, it doesn't change. It's negative fx. From B to C, it's negative fx minus q times the x minus L over 2, right? So we're only dealing with this portion here. And so for the A to B portion, we're going to take the derivative of the bending moment with respect to q in both of these segments, and it goes to 0. And here it goes to negative x minus L over 2. And so let's look at what this looks like plugged in. We have our 0 to L over 2 component of the integral, where my derivative goes to 0, so this is going to go away, which is kind of what I would expect. The inertia from A to B is not impacting how much B is deflecting, even as the force is being transferred through AB. And so then the second half, from L over 2 to L, we have our larger inertia. We have minus fx, and then we have minus, this is the derivative, x minus L over 2. We will integrate that portion, and the delta B is now known. And so, so that is one way of dealing with this kind of deflection analysis. And then in the next video, we'll take a look at example 411 in more detail.